Now let us try to find the magnetic field intensity due to infinite sheet of current with the help of Ampere's law. So for that purpose, let us consider the coordinates x, y, z, and the plane in which the plane or the sheet in which the current is flowing. Consider the z is equal to 0, it means xy plane. The current is flowing in the y direction like this. So the sheet is there, the direction of the current is in the direction of y. So in this case we have to find the magnetic field intensity due to this sheet. For that purpose, we can assume there are infinite number of filaments, and from each filament we have to find the magnetic field. We can consider that there are infinite number of filaments, and from each of them we can consider the magnetic field intensity at any point, and that will give us the cumulatively from full sheet. So for that purpose, we have to assume Amperian path in the first. So Amperian path you can assume rectangle from which the sheet is passing. Half part of rectangle is, we can consider like that. We can name it 1, 2, 3, 4. Half of the rectangle is above the surface sheet, and half of the rectangle is below the sheet of the current. So this is the structure. Now if we will find the magnetic field intensity due to, this is considered as Amperian path. From single filament we will find the magnetic field intensity, then we can find from all of them. As current is in the direction of y only, so we can say Js will be nothing, Jsy in the direction of Ay. We can write like this. And field from the previous study we know that is I, that is the product of dl cross r. This is the field. So here consider one element. This is dl, in which current element is dl, idl. R is, for example, at the top, then dl cross r, so it should be towards x. Consider this in the direction of y, and if it is in the direction of above, then dh will be in the direction of x, in this direction. So it should be it is just proportional to this. We can say it is h naught in the direction of ax. We can say h we don't know, just this is maximum, any h in the direction of ax. Consider in the bottom side. In the bottom side it will be in the direction of negative x, in the direction of current. Curling finger will give us the direction of the field, so that will be, it will be in the direction, if z is equal to more than 0 above the surface, and when this lies below the surface, then it will be minus ax, that will be this. So h will be this, for you can say like this. We don't know h right now, but we can have the direction of h in the direction of x only and minus x only. So from this setup we can find that when z is positive, in that case z means the Amperian path is the point of interest where we have to find the magnetic field intensity. When z is more than 0, in that case the direction of the field magnetic field intensity will be x. When it is less than 0, it should be minus x. So one thing becomes clear from here. Now consider the Amperian path. This is point 1, this is point 2, 3 and 4. Now for all the cases, try to find the enclosed current, that is H dot dl. So for this portion from 1 to 2, the H is in the direction of plus AX. So we can write H naught in the direction of plus AX for this portion, and dot dl will be a by 2 for this portion in the direction of minus az. So a by 2 in the direction of minus az with minus sign. So either minus or plus. Apart from that, the dot product of ax and az will give you 0. So don't worry about this term at this moment. So next will be h dot dl for, because this is 0, so and next is from 2 to 3. H is in this direction, that is h naught in the direction of positive ax, dot dl will be b opposite to the positive direction. It is moving in the opposite direction. So you can say b in the direction of minus ax. So you can write b in the direction of minus ax. Okay, and what's about h? H is positive in this direction. However, this direction is considered as negative. So it should be minus ax direction. So if for 2, it will be minus h naught ax dot b in the direction of minus x. For this case, from 3 to 4, same way, this is in the direction of positive az, and the h will be either in this or this, so in the direction of x only. So from there we can say the dot product of z and x will give us 0. For this region, h is in the direction of ax and dl will be in the direction of full length. It will be b in the direction of ax. This is the integration b. This is the full integration for full length. So next will be, this will be 0, this is 0, this will be h naught b ax dot ax will give us 1, it will be h naught b. So this is the total enclosed current in the case of this Amperian path. If the current is given in the direction of y, J is y in the direction of y, then for this Amperian path, the current enclosed will be, we can say the current enclosed will be this times this length, as it is moving in the direction of y only. So we can say J is y and this length is b. So this will be current enclosed by this Amperian path, and this should be equal to this. So 2H0B will be equal to the JSYB, and H0 from here we can say JSY by 2. Now put this here, H will be H0, that is JSY by 2 in the direction of AX for the Amperian path above the sheet, and JS by 2 in the direction of minus AX for below the sheet. So in this way we can say H is given for the sheet which is having the current density JSY in the direction of Y. In general, for an infinite sheet of current which is having density J can be written as J cross AN. The cross product will give us AS, we have seen here. J cross AN is equal to H, half term will be included. So this is the general form of H for an infinite sheet of current, where AN is the unit vector from the current sheet to the point of interest, and J is the current density. So this was the finding the H with the help of Ampere's law, for infinite sheet of current. Now let us solve one example based on the sheet current to find the magnetic field intensity at a given point. The problem is planes Z is equal to 0 and Z is equal to 4 carry current K is equal to minus 10 AX and K is equal to plus 10 AX ampere per meter respectively, and we have to determine H at this point that is having coordinate 1, 1, 1, and another point which is having coordinate 0, minus 3 and 10. So according to the problem statement, let us have Z is equal to 0 and Z is equal to 4 planes. Z is equal to 0 carry current inward minus AX direction. This is Y, this is Z, and X is inside as the coordinates are orthogonal. So inside it is considered as negative, outside it is considered as positive. So at Z is equal to 0, it is going inside. So the current is going inside at this point in the minus AX direction, and the current density at Z is equal to 4 is 10 magnitude in the direction of plus AX, that is outward. That's why it is indicated by dot. Now we have to find the H for case A. For case A, the point of interest 1, 1, 1 lies, means in XY plane it is 1, 1, and Z is equal to 1. So Z is equal to 1 means the point lies between this region, somewhere here, for example. So if P lies inside the two sheets carrying current in opposite direction, then we can have the magnetic field intensity at this point that will be equal to the intensity due to this and intensity due to another one. So intensity due to Z is equal to 0 sheet and intensity due to the sheet which is having at level 4. Okay, so these two vector sum of these two will give us the total magnetic field intensity. So for this point, for point A, in the case when P is 1, 1, 1, then we are talking about. In the beginning, for the sheet current, we have derived that H was equal to the half the current density cross the normal vector. We have derived this already. So from there, we can say for H, this current sheet, H naught will be half. For this one, it is going inside, so K is minus 10 in the direction of inside AX, so minus 10 AX, and AN is the normal vector to this direction. This is Z direction, this is Y direction, and this is X direction, minus X direction. So if we have considered this, according to that, AN for this point will be plus AZ, okay, and the cross product of AX and AZ will give us from here X, Y, Z, like this. So AX and AZ will give us minus AY, because this is positive. So from here we will find minus 5 AX cross AZ minus AY, and from here we will get 5 AY. Similarly, for another sheet current, we can find that is named H4 due to the level of the sheet, and again we will apply same formula, K cross AN, and K is how much? 10 AX. So half 10 AX, it is already given, cross AN will be below this because Z is equal to 1, so it should be in negative direction. According to that, it will be in minus AZ direction. Hope it is okay. So from here we have this term will be 5 AX cross AZ, again it will be minus AY, and that minus and this minus will be plus. AX cross minus AZ will give us AY with plus sign. So H0 is this and H4 is this. And if we wish to find the total H, then it will be H0 plus H4, and from here 5 AY plus 5 AY, it will give us the total intensity at this point. This is P111 at this point. So H is this. Okay. Now consider the case B, where point of interest is 0, -3 and 10, as it is written here. In this case, the point is lying, Z is equal to 10. So point is lying somewhere 0, 4, 10 outside of these planes. So somewhere here. So according to that, for example, the point of interest in this case is here. In that case, H will be H0 plus H4, similar to previous one again, and H0 will be similarly from here half K cross AN, and K is, for not case, K is minus 10 AX, minus 10 AX, and cross AN will be plus AZ. See, we are at this point now, that is 10 unit away from here in the positive direction. so it is in the z direction. Okay, and if we will solve this, ax cross az will give us minus ay, so minus and minus, it will give plus, so it will be plus ay. And h4 in this case will be, this is again in the direction of plus az, so k is 10 ax. For this case the density is plus ax, so k times the point is again in the positive z direction, so it should be plus z. From here it will be 5 ax cross az will give us minus ay, so from here we will get minus ay. So total h will be h0 plus h4, that is 5ay minus 5ay, that is 0. So we find that inside the parallel sheets of opposite current density, means if in from one the current is going, second is having a return path for that current, in that case the magnetic field intensity out of this sheet will be 0. There will be magnetic field intensity only inside. Okay, so in this case h is equal to 0. If we summarize our study regarding Ampere's law and its applications, then we can say we have discussed Ampere's law, and it was h dot dl was equal to the I enclosed. This was the integral form of Ampere's law. At the same time, we have seen that del cross H was equal to the current density. It was the differential form of Ampere's law. Next that we discussed was, in case of infinite line conductor, the magnetic field intensity at any point was equal to the I by 2 pi rho, where rho was the perpendicular distance from point to the line conductor. Third thing we discussed, infinite sheet having current. In that case the magnetic field intensity was half the intensity density cross AN and minus half, keep it plus, for minus AN. This was the Amperian path that was above to the sheet, and this was due to the Amperian path below to the sheet. So we can say it was at the above to the plane, it was below to the plane. And the next we discussed coaxial case. There was two conductors and the coaxial transmission line was there. In that case we tried to find the magnetic field intensity at different regions in the surrounding of the cable, and we obtained that the field at outside was equal to the 0.